Hello, welcome to my video series of data structures. This is part 1 of Module 5, the tree data structure. In this video, we will introduce the fundamentals. We are familiar with trees in nature, and the tree data structure shares a similar concept. However, the tree data structure is typically represented upside down, with the root at the top and the branches extending downward. In the tree data structure, nodes are connected by edges. Similar to natural tree, there is one special node from which all other nodes originate. This special node is called the root, and it is highlighted in red in the figure. Nodes at the lowest level of the tree are called leaves, which are colored blue in the right figure. Other nodes that are neither roots or leaves are called internal nodes, and they are colored orange. The nodes are connected by edges, represented by the black arrows. The edges are directed, pointing from a shallower node to a deeper node. We define the depth of a node as the number of edges between that node and the root. For example, the root A has a depth of 0, and the node B has a depth of 1. On the other hand, the height of a node is defined as the maximum number of edges between that node and a leaf node. For instance, the root node A has a height of 3, with the path passing through the edges AB, BD, and DE. A shorter path from A to a leaf node is AC and CG. However, since we are interested in the maximum number of edges to any leaf, the height of node A remains 3. Similarly, the height of the node B is 2. The depth of each node naturally defines its hierarchy within the tree, making the tree data structure an effective way to store data that has hierarchical relationships. When two nodes are connected by an edge, the node with the smaller depth is referred to as the parent, while the node with the larger depth is called the child. For example, node A is the parent of B and C, and nodes B and C are the children of node A. Nodes that share the same parent are known as siblings. For example, the nodes B and C are siblings. In the case of any two nodes that are connected, whether directly or indirectly, the shallower node is called the ancestor of the deeper node, and the deeper node is the descendant of the shallower node. For example, node A is the ancestor of node E, and node E is a descendant of node A. Each node can have 0 or multiple children, but it can only have 0 or 1 parent. This restriction creates a structure that resembles a tree fanning out from its root node, in general with more nodes in the lower levels than the higher levels. Thus, the tree data structure is similar to an upside-down natural tree. With the basic concepts in place, we can now formally define the tree data structure. A tree is a collection of nodes, which may be either empty or non-empty. If the collection is non-empty, it contains a distinguishing node called the root, denoted as R, and 0 or more non-empty subtrees whose roots are children of R. It is important to know that this definition is recursive. For example, consider the node A as the root of the tree. Its two non-empty subtrees, T1 and T2, have their root nodes, B and C, as the children of A. Recursively, the subtree T1 is also a tree. It has a root B and a non-empty subtree T11. The root of the non-empty subtree T11 is D, which is a child of B. Once we reach a leaf node, the node itself serves as a root of the tree and has 0 subtrees attached to it. Finally, it is important to know that an empty tree with 0 node is valid according to definition. The tree data structure is commonly used to store data that contains hierarchical relationship. For instance, it can represent structures such as directory hierarchy, a family pedigree, evolutionary history, or a company organization. The figure below illustrates a typical Windows directory structure. For example, under the root directory, cdisk, there is a subfolder called users. Within the directory C, users, John, there are several subfolders, such as desktop, documents, downloads, and music. Here is the declaration of the tree node structure in C++, which represents a node in a tree. The first variable, element, is used to store the data associated with the node. For example, in the case of representing a directory structure, element could be a string type that holds the name of a folder or file. It could also be an integer or any other type of object you define. The second variable, firstChild, is a pointer to another tree node, representing the edge that connects the node to its leftmost child. If the node has no children, this pointer will be set to null. The third variable, nextSibling, is also a pointer to another tree node, pointing to the next sibling of the current node. If there are no more siblings, this pointer will be set to null. We use this implementation instead of defining multiple pointers for each child, as each node can have an arbitrary number of children, making it impractical to predefine a fixed number of pointers. By using this structure, sibling nodes are implicitly organized as a linked list, with the first child pointer serving as the head of the list. Here, we present both the conceptual tree and its actual implementation. Note the differences highlighted by the sign edges, which correspond to the next sibling pointers in the implementation. The fundamental operations of the tree data structure include traversal, searching, inserting a node, and deleting a node. In this video, we will focus on two methods for traversing a generic tree structure. The operations for searching, inserting, and deleting nodes can vary depending on the specific subtype of the tree. We will explore these operations in more details within the relevant context. In this video, we will focus on introducing pre-order and post-order traversal. Note that these are not the only ways to traverse a tree. Other methods, such as in-order traversal, will be introduced in their specific context. Pre-order traversal visits the parent node first, followed by its children. In contrast, post-order traversal visits the children first, then the parent node. Note that the visit orders are defined recursively, as we will demonstrate with the following examples. Pre-order traversal is useful when you need to access the information from higher levels of the hierarchy first. For example, if you want to construct the full path of a folder or file from a tree representing a directory structure, pre-order traversal will be the appropriate choice. This is because When constructing the file path, we need to obtain the directory names from the higher levels of the hierarchy first. Say we have the tree shown in the figure here. The pre-order traversal starts at the root node. Since we visit the parent node before its children, we can access the information stored in the current node immediately. In this case, we output the information stored in the node, which is John. To indicate that the node is being visited, we will mark it in red. Next, we move on to accessing the children of John. We encounter the subtree rooted at Documents. Since we visit the parent first in pre-order traversal, we can immediately output the information Documents. Next, we access the child of Documents and output app.cpp. At this point, there are no further nodes to explore beneath app.cpp. Therefore, we return to Documents to visit any remaining unvisited children. Next, we visit app.h and output the information. After visiting app.h, we have completed visiting all the children of Documents. Now, we return to John and visit any remaining unvisited children. Next, we visit Downloads and output the information. We proceed to visit its subtree, smurf.mp4, and output the information. At this point, we have visited all the children of Downloads, so we return to visit any remaining unvisited children of John. Next, we visit Music and output the information. Finally, we visit the last node, jazz.mp3. At this point, the traversal is complete. Here is the pseudocode for pre-order traversal. In line 3, the current node is visited, and its information is printed. Lines 6 and 7 recursively visit all the children of the current node. Note that visiting the current node, as done in line 3, occurs before visiting its children, which is done in lines 6 and 7. This is why we call this traversal order pre-order. Now, let's take a look at post-order traversal. Post-order traversal is often used when we need to access information in lower level nodes before accessing information in higher level nodes. One common application is calculating the disk space occupied by a folder. To do this, we need to sum the sizes of all the files stored under the folder of interest. Since the files under the folder correspond to descendants of the folder in the tree structure, post-order traversal is necessary to visit the files first. Let's consider the same directory tree again. Note that we have now included the sizes of the files in this tree. Post-order traversal also starts at the root. Since we need to visit the children before visiting the current node, the node John is not accessed at this point. To indicate that a node is being considered but not yet visited, we will bold its box while keeping its original color. We proceed by considering the first child of the root node. For the same reason, we do not access its information at this point. Next, we consider the node app.cpp and find that it has no children. In this case, there is no need to visit any children, so we can proceed with visiting this node. We then record the size of app.cpp. To indicate that the node has been visited, we color it red. After visiting app.cpp, we know that the node has other siblings. In post-order traversal, we must visit all the siblings before visiting the parent. As a result, we proceed to visit the sibling of app.cpp, which is app.h, and record its size. Now that we have visited all the children of documents, we can visit the node itself. Since documents is a folder, we compute its disk space consumption by summing the sizes of all its children. In this case, the disk space occupied by documents is 105K. Then, we consider the next sibling of documents, which is downloads. Since this node has a child, we must visit its child first before visiting the node itself. We proceed to the child of downloads and reach smurfs.mp4. Since this node has no children, we can visit it directly and record size. After visiting smurfs.mp4, we have visited all the children of downloads. As a result, we now proceed to visit downloads itself. We calculate the disk space occupied by downloads by summing the space used by all of its children. Next, we consider music, the next sibling of downloads. Since music has a child, we will not visit it immediately. We visit its child jazz.mp3 and record the size. We return to the node music and calculate its total disk consumption. Finally, after visiting all the children of the root node John, we can visit the node itself. We calculate its total disk consumption by summing the disk space used by all of its children. We find that the folder Join occupies 1 GB, 5 MB, and 105 KB of disk space. Here is the pseudocode for the post-order traversal of the directory tree. In line 3, we initialize the space consumption using the size of the current node. Lines 6 and 7 recursively visit all the children of the node and sum their respective sizes. Line 9 returns the total space consumption of the current node. Since the total size of the parent, calculated in line 9, is accessed after the total size of the children, calculated in line 7, the order is considered post-order. In this video, we introduced the fundamentals of the tree data structure. We covered key terminologies such as root, leaf nodes, internal nodes, parent, child, sibling, ancestor, descendant, and subtree. We have also formally defined the tree data structure. Additionally, we discussed the implementation of a generic tree data structure, where siblings are organized as a linked list, and the head pointer is stored in their parent node. Finally, we introduced two tree traversal methods, pre-order and post-order. In addition to traversal, we also need to consider other important operations such as search, insertion, and deletion. However, the current tree implementation does not guarantee optimized performance for these operations. This is because we need to revisit all elements to identify the one of interest, which takes linear time O(n), where n is the number of data elements. In the next video, we will introduce the binary search tree data structure, or BST, which improves the average search time complexity to O log n. Thank you for watching, and see you next time.